looking at my scribbled notes, which unfortunately aren't that neat. But anyway, so the idea is that in an asymptotic expansion at very high energy, you see the normal formula for the cosmological term and the Einstein-Hilbert term, and lots of other terms like the standard model. But they're not fundamentally baked in the theory. So it's asymptotic, but they're not, the actual theory isn't built from them in the first place. Okay, so this is the formula I want to prove, which is on the left here, I've got a formula involving an integral over Lorentzian geometries. So GL is the space of Lorentzian geometries, and ML the space of Lorentzian matter fields. And so schematically, I've got e to the I times some Lorentzian action integrated over all those fields. And on the right, I've got the same thing, but for Euclidean geometries in Euclidean matter fields. So we've got an integral over Euclidean geometry, whatever that is, and Euclidean matter. And the idea is that on the left-hand side is real physics, and we know what everything in there should be. You can open a textbook. And on the right-hand side, of course, we don't know what it is and should be because we don't live in the Euclidean universe. So the right-hand side is whatever emerges from doing this, from proving this theorem. And there are, in real situations, there are typically boundary conditions, but I'm not going to bother myself with those. So the simplest case would be a manifold without boundary, I guess, but more realistically, there'll be boundaries and possibly observables to take care of as well. Okay, so various issues with this. Firstly, the functional integrals are heuristic. And as I said before, therefore, we can't make this precise mathematics. The Euclidean Einstein-Hilbert action is not bounded below, and that's always been cited as a reason why the right-hand side of this is badly defined. And people then historically tried to maneuver around sidestepping that. So they're thinking that the Einstein-Hilbert action is fundamental, and of course they have this problem, which I'll say more about in a minute. But there's also the Planck scale, and there's to reckon with. And we should think of the Planck scale as possibly a cutoff. I mean, physically, it's a unit of length, which is root g h bar. And there's either new mathematics at this scale, and I like to think it's non-commutativity, although it might be something else. And most likely there's new physics at this scale. We certainly know that the old physics doesn't work at the Planck scale. And so there's some sort of new physics or new mathematics or something. Okay, so that's the issues. And here's my sort of very rough proof of this formula, which I had on this slide here. I want to think of these as huge multi-dimensional contour integrals, and I'm going to rotate the contour integration. So this is a schematic for doing this. So I embed GL, the Lorentzian geometries, into the CL, the complex Lorentzian geometries, and think of the whole thing as some contour integral. And then I want to rotate the contour to a new contour, GL prime, which I'm calling the imaginary Lorentzian contour. So it's some contour in Lorentzian geometries where some things are imaginary. So this is the schematic here. Can you see the hand on my PDF or not? So if I move it, can you see that?
Yes, we do see the hand. And yes, so I'm welcoming more participants that probably were on some other, former older link, but they are joining us now.
Okay, great. So, well, you haven't missed very much, just the explanation of what the talk was about. Yeah, so here we are rotating the contour from the real Lorentzian geometries to the imaginary Lorentzian geometries here. And the idea is that you should somehow complete this with a circle at a large radius as normal, which will vanish as you might take the radius infinity, thus giving a proof that this functional integral along here will be equal to that functional integral along here. And the final step is that when you've got this imaginary Lorentzian contour, you need to prove something I want to call Euclideanization, which is that there's a one-to-one correspondence between the imaginary Lorentzian geometries and the real Euclidean geometries. So this result I'm trying to prove is a two-step process here. So we start with the integral of the Lorentzian functional integral over real Lorentzian geometries. I rotate the contour to the imaginary Lorentzian geometries, and I then identify everything in that calculation as the integral over Euclidean geometries. Okay, and I've talked just about geometries here, but I also meant and matter fields. So you can go through this whole story again and include matter fields. And the scalars, in fact, are unchanged in this process. If you have a vector field, there's perhaps the components have to have rotation in an imaginary direction, and spinors I'll talk about a bit later. Okay, so that's that. And then this is just general yoga about contour rotations in C, the ordinary complex numbers. So this is the standard result here, which is that if you take an oscillatory integral here, e to the ikx, with k some constant, and m of x some function, then if m of x behaves suitably, you can then analytically continue everything and integrate not along the real axis, but along the imaginary axis here, and complete it with the contour at infinity. And as long as the sup of m goes to 0 on that, Jordan's lemma tells you that this goes to 0 when you have a large radius. And taking that limit gives you a definition of what the Lorentzian integral is, because it may not be absolutely convergent. But you can take the limit exactly on the Euclidean integral, and you just get the integral here all the way to infinity. Okay, and then you can extend that. So k was a constant, but what I want to do here is have e to the iw of x, where w is some function, and I simply change variables to w, and then I'm back to this constant situation of k1 with 1 over some derivative, which will be our m function here. So you can see that if w behaves in the right kind of way, this thing will satisfy Jordan's lemma, and you can do a similar game for these sorts of oscillatory integrals here, going to some real slice. And I want to think of this in the multiple integral sense. All the multiple integrals are the same R, but some very large dimensional version of this same result. And of course, you can go back and think about, how to apply this to my formula here and sketch a proof. And it depends on what you think the action is, of course, and whether it has all the properties you need for it to have. And you can look at the Einstein-Hilbert action and so on and ask, does it have the right sort of behavior at small and large metrics and degenerate ones and so on? I think it's a bit of a fruitless project in a way, because the integral is heuristic, and B, it's certainly true that when you get to the Planck scale, which is certainly going to be one end of the integration, then whatever happens there isn't going to be the standard Einstein-Hilbert action. It's going to possibly involve higher curvature terms. They could easily come in at the Planck scale, or possibly different mathematics. So I'm going to park the question about whether one could tighten up this proof and apply it rigorously for a different mathematical setting. So perhaps when we get to the full non-commutative geometry, then it's worth revisiting this proof. So at the moment, it's sort of heuristic idea and a way of setting the thing, and I'm going to leave it there for the rotating the contour thing. But I want to talk more about the Euclideanization a bit later in the talk. Okay, so that's that, and here's the history. So I want to talk about this because you see, the whole way in which this talk started was I was explaining to my student Alex why it is we're so interested in Euclidean quantum gravity and Euclidean physics, and how you connect it with Lorentzian real physics. And the more I tried to explain it, the more I realized there's sort of a gap in the sort of understanding of the way this works. So the purpose of giving this talk is to sort of try and fill in, at least conceptually, some of these gaps. And I think when I went back and looked at Hawking's work, he doesn't quite do what I thought he did at the time. So let me explain a bit by showing what it is and what perhaps it might have been but wasn't. So here I think is the first ever discussion of Euclidean quantum gravity from 1977. And this is in fact page 2. And he talks about quantum gravity on a space-time with initial slice sigma I and a final slice sigma f, and possibly some boundary surface at infinity. And then he says it's convenient to rotate the time interval in this time-like tube so it becomes purely imaginary. This makes the metric on the boundary positive definite, so the path integral can be taken over all positive definite metrics. So what he's doing here is saying, okay, this integral over positive definite metrics is now my definition of quantum gravity. And then a bit more history here. A little bit later, this is early in 1978, Gibbons, Hawking, and Perry, they say, oh, well, actually, there's a problem. The problem is that the Euclidean action for gravity is not positive definite. And because conformal transformations can make the action arbitrarily negative. And in order to make the path integrals converge, you have to take a new contour of integration for the conformal factor. You have to make that imaginary. So this is a bit of a setback in a way. So the nice clear idea of e to the minus Euclidean action kind of gets a dent in it. So let me explain more what the problem is. So there's a bit more from Gibbons, Hawking, and Perry. So you see at the top here, the standard Einstein-Hilbert action. And it turns out that in Euclidean signature, there's a minus sign in front of it. And now they do a conformal rotation. So that's G is omega squared, G tilde is omega squared G. And then this action here becomes this thing here down 1.6. The scalar curvature gets multiplied by omega squared. Okay, fair enough. But then you add a term, which is the gradient of omega all squared. And this being Euclidean signature, that's positive, and there's a minus sign out in front, so the whole thing is as negative. And then he says you can make it as negative as you want by choosing a rapidly varying conformal factor. So, oh dear. So e to the minus a negative action is bad news because that's very big. Will kill the convergence of the thing. But, of course, now we're trying to think about cutoffs and Planck scale and so on. The Planck scale limits the frequency. So you can't make this thing as negative as you want by choosing a rapidly varying conformal factor because there's a limit to the frequency in which it can vary, and that's the Planck scale. So in actual fact, the action is bounded below. And in fact, if you look at the Kohn-Shamsuddin action, that's in fact positive. So if I go all the way back to that, wherever it was, yep, here. So this formula here for the bosonic part, the trace of an operator square, that is greater than or equal to 0. Einstein-Hilbert still appears in the asymptotics of it, but it's not fundamental to the construction. So obviously what's happening is that whatever goes negative here is cancelled by something that's also positive, probably the cosmological term here. So quite how realistic this is, or whether it's ameliorated by a renormalization group, who knows? But at least it's not true that one has to worry forevermore about the Gibbons, Hawking, and Perry problem that the action is unbounded below. Okay, so with that, I want to then talk about the relation of what I'm talking about to Wick rotation. And I want to say that what I'm talking about is not Wick rotation. So weak rotation. So here's weak rotation. So I've got, again, my real axis here of Lorentzian geometries. So there's a particular point there, that blob. And here's my imaginary axis, which corresponds to Euclidean geometries. And weak rotation is the process of taking one of these and trying to match it to one of those. And that is absolutely not what I'm doing. So there's no sense in which there's a good correspondence between a point on one contour and a point on the other contour in my language. The metrics are physically different. They have different properties. For example, if you do quantum field theory, down here this blob would be Minkowski space, and up here this blob would be Euclidean space. And quantum field theory, even a scalar quantum field theory on one is completely physically different to one on the other. Yes, when you measure some things, you can analytically continue in some parameters if you're lucky, and get results that way, but they're not the same thing. Whilst weak rotation is this process of looking at physically different particular metrics, I'm looking at a completely different thing, which is trying to prove that two contour integrals over lots of geometries are, in fact, exactly the same. And there's no sense in here in which one point in here corresponds to any particular point or contribution in the other integral. Okay, so it took quite a while to slay that particular demon. Right, so on to talking about a bit more history. Now we come to 1978, and this is from Hawking's Cargès lectures, presumably in the summer. I don't know exactly when the conference was. I can't look them up anymore. But again, it's fairly early in the development of this theory, so I think it indicates what he was thinking at the time. So what happens is on the previous, this is about page 3 of this paper, and on the previous 2 pages is a discussion of weak rotation of quantum field theory, which introduces a Euclidean approach. And then he says, I feel one should adopt a similar Euclidean approach in quantum gravity and supergravity. Of course, you can't just replace the time by imaginary time because there's no preferred set of times. And then he says, instead, I think one should perform the path integrals over all positive definite metrics, most of which won't be have a section in which the metric is real and Lorentzian. In other words, there isn't a weak rotation one-to-one between Euclidean and Lorentzian. So that's good. That's what we believe. And work since then has shown that yes, that there are weak rotations of some spacetimes, but not all. There's some condition on the curvature tensor. Okay, so that's that we understand. And then analytically continue the result of the path integral if necessary. So in other words, he's thinking of this Euclidean quantum gravity as a sort of definition of what quantum gravity is. And whatever you've done, you've measured something, perhaps some observables, and you then might analytically continue in those parameters, or perhaps the boundary, as I drew earlier, to get back to Lorentzian time, for example, on the spatial infinity. So really, that seems to be the way the theory developed. And I have to say that wasn't quite what I understood when I arrived later on the scene. I mean, I started my PhD in 1982, and this was already been going a few years. I didn't get to Cambridge till 1988 and joined Stephen Hawking's group. And this kind of thing was still going on, but it was pretty mature by then, and people were talking about, how to cope with anisotropic cosmologies and things. So the roots of it were still discussed, but it wasn't, people weren't really focusing on that at the time. But what I picked up from there is I thought that people had in mind some sort of result like I've written down here, that there was a Lorentzian path integral and it really was equal to the Euclidean path integral. And we were doing the Euclidean path integral because that's more convenient or better defined or something, or better convergence properties. So I spent many years thinking that this equation here was at the back of people's minds and was sort of the motivation for everything that was done. So it's a bit of a shock to go back and discover that it wasn't, and there was no kind of statement of this formula like this. And then perhaps it does seem to be that what people were doing was a much lesser project, which was just trying to find a definition at all. But of course, this doesn't really make sense if you define your physics in the Euclidean regime, and it doesn't then come back to giving you the right Lorentzian physics that you want to simulate in Lorentzian regime. And if that didn't work, then the whole program would be nonsense. So it seems to me that there must be some sort of result like this, if only one could come out and state it. So that's what I'm trying to do. Phew. Okay, so that's the overall stuff. So now into a bit more of some detail here. Hawking says what you should do is consider the metric to be the square of a tetrad here, because then you get metrics that only have Euclidean signature or possibly degenerate, but you don't get the other signatures. So I'm going to take that approach too, but in fact not use his tetrad field, but use the inverse, which is commonly called a frame field. So before I dive into this, anybody got any questions so far? I feel like I've been going on for ages.
Any questions?
Okay, well, if not, I can carry on.
I have a question.
Yeah.
Hello. Can you please just give the explanation once again? Give the argument. What is the difference between the Wick rotation and what you are trying to do? Because the way I learned about Wick rotation in textbooks is precisely performing the contour integral that you are doing, right? So in what sense is this different from? I didn't catch the difference. That's
yeah. Well, Wick rotation is often used rather loosely to mean various different things. In fact, so people sort of use the phrase a bit casually. But when you look precisely what it means, people mean you take some Minkowski geometry, for example, a black hole, and you associate it to a Euclidean geometry. For example, a Euclidean black hole. Euclidean Schwarzschild is the Wick rotation of ordinary Schwarzschild. And then then of course you can do physics on those two space-times, and you might then try and relate them. You might say, well, okay, so is something as the mass function, the mass parameter in one space-time the same function as it is in the mass parameter in the other space-time? The answer is no. And you say, well, is it an analytic continuation of it, or is it some relation or something like that? So that's what I understand as the real meaning of Wick rotation. It's physics on, and that's certainly what people do in quantum field theory. They do physics on Minkowski space and relate it to physics in Euclidean space. So very two definite actual spacetimes. Okay, anything else? Good, let's carry on. So here I am talking about frame fields, and so I've got some four manifold, and there are four vector fields on it, L0, L1, L2, and L3, forming an orthonormal Minkowski frame. And a spin connection, nabla, and I'm using the Minkowski metric here. So that's the metric appropriate to those indices here. So this one, L0 is time-like, and L1, L2, and L3 are space-like unit normal vectors. And then certainly in the non-degenerate case anyway, when these form a proper frame and not a collapsed degenerate one, you can define functions sigma, which are like the spin connection coefficients, and some other coefficients telling you what the commutators of these vector fields are. And then you can calculate everything you want. For example, the curvature I've done here, yeah, that's just about all fitted on the page. Yeah, that's right. So it comes out in terms of differentiating these spin connection coefficients. That's what this L of this means, and products of them. A familiar formula, but just to show you that everything can be calculated in terms of these coefficients. Okay, so then we can go to our imaginary contour, which so what is it here? Well, I take the zeroth vector field to be I times the a real, so the E's are real in this formula. E0, E1, E2, E3 are real vector fields. So L0 is I times it, so that's an imaginary vector field. And L1, L2, and L3 are real vector fields. And similarly with the sigmas, the spin connection coefficients, they're some power of I times omegas, and omegas are real. So the idea is that E and omega are going to be the Euclidean geometry and the Euclideanization. But for these imaginary things, this is the imaginary Lorentzian geometry. Okay. And you can work out the formulas for the action. The Lorentzian action is this formula here. So it's -2 lambda plus the Lorentzian scalar curvature. When I don't put an index on something, it means Lorentzian, that's default. D volume, D Lorentzian volume, and of course the matter fields, say for a scalar. And here's the Euclidean action. It's actually the sign reverse of these formulas, but here this is the Euclidean curvature. So it's different. It involves the Euclidean metric and not the Minkowski metric. And the Euclidean volume formula, and then the Euclidean action for scalars, which again has different signs in it, because you're using the Euclidean metric, not the Minkowski metric. And the result of how these are related is that if you go onto this imaginary contour here, then these are very simply related. Well, here it is. I times the Lorentzian action on this imaginary contour is equal to the Euclidean action. And that's what I mean by Euclideanization here. And this is well known. This goes from Samuel and more recent paper of D'Andrea, Kirchhoff, and Litzy, has all these exact same calculations in it, but for a different purpose. They were talking about Wick rotation, which is almost what I'm talking about, but not quite. And I believe their project was to start with a Lorentzian metric and associate it with it a Euclidean metric. But that's not what I'm doing. I'm just looking at this imaginary contour and saying, oh, well, this has a good interpretation in terms of Euclidean geometry, and it's part of what these people did here. And by the way, I think these calculations are well known going back, and certainly seems to be what Gibbons, Hawking, and Perry knew, although they don't spell out the details of the calculation. They certainly seem to know that this formula turns into that formula, and they mumble something about Wick rotation in their paper to justify this. So perhaps when they were doing it, they had some particular metrics in mind. I'm not exactly sure. They don't give any details for this. But the way I've spelled it out, it is a calculation. It's in a couple of pages of calculation. It's not just obvious that this result here, this is the Euclideanization result. So on to the technical part of the talk. The only place where I really think I've, apart from setting the whole thing up, where I really think I've done anything technically new, here is the discussion of spinors, which I think is a bit different from other discussions of spinors. So this is just to set up what's going on here. Here's a spinor in C4, and I'm starting with the Euclidean inner product. So that's the one the obvious one where it's just the Hermitian dot product of two four-dimensional vectors, and it's positive formula, positive Hermitian. And then the Lorentzian formula, as per textbooks, you take the Euclidean formula and you put a gamma 0 in the formula to make it indefinite and be invariant under the Lorentz group. And that's the inner product there. You'll notice there's no subscript. So as I said, by default, things are Lorentzian if there's no subscript. The gamma matrices here, these are the Lorentzian gamma matrices. And notice there's a minus here. So the gamma 0 squares to +1, as you find in the usual physics textbook. The chirality operator here is squares to 1, and the plus and minus 1 eigenspaces are the left and the right particles. And there's a charge conjugation, which is an antilinear operator on these spinors. And this is physics, so it squares to 1 and it anticommutes with the chirality. Okay, so that's just spinors. And then we can do spinor fields on a manifold. So these are fields here. So the angle brackets is the inner product on these fields here. And this is Lorentzian here. So I'm integrating over the whole manifold, the Lorentzian inner product with the volume form. So this is an indefinite inner product here. It's sesquilinear, but indefinite. And here's the Dirac operator. I put an I in the formula because of the usual physics conventions, I gamma A, and the covariant derivative in the LA direction. Okay, and then you can show that this is Hermitian with respect to this inner product and commutes with the charge conjugation operator. Okay, so that's fairly straightforward. How am I doing for time? Yep. So I'm sort of fairly rushing through this despite the glitches on the tech front. It's probably because I'm not writing anything, so you're probably all would have been better if I'd slowed down by writing some things, but I've got nothing, no way to write at the moment. Okay, so so now Euclidean spinors. So the spinors are the same, but conjugate fields are tricky, so you have to watch out a bit. And the chirality is the same, which is perhaps a surprise, and it certainly contradicts what people said back in the 70s and 80s about analytically continuing spinors. There's a different charge conjugation operator, and in fact, this is a good one, which is you just take the Lorentzian one and multiply by gamma 0, and that turns out to have all the right properties of the Euclidean one. For example, JE squared is -1, and it also anticommutes with the chirality operator. So that's symptomatic of KO dimension 2 for non-commutative geometry people, whereas the Lorentzian one here, because J squared is 1, that's KO dimension 6. So we're changing KO dimension. I think I've forgotten to write the gamma matrices on. I was probably going to write them with a pen. But the Euclidean gamma matrices, did I write them on? No, I didn't. The Euclidean gamma matrices, gamma 0 Euclidean is I times gamma 0 Lorentzian, and the other gamma matrices are the same. So when you do that, you can then define the Dirac operator for the Euclidean regime. And this is using the Euclidean gamma matrices and the Euclidean covariant derivative, which is gotten by doing the rotation of the spin coefficients here. So recall, I'm on my imaginary Lorentzian contour, and then the Lorentzian spin connection defines the Euclidean one by its I times some real Euclidean coefficients here. So these are for the Euclidean group here, whereas these are for the Lorentzian group. So that's the formula for the Euclidean Dirac operator, and there's no I in this formula, and in fact these are the right have the right properties for a Euclidean Dirac operator. So they all of these gamma matrices all square to -1. So this is the right formula for a Dirac operator without an I in it. And indeed, you can prove that this formula is self-adjoint using the Euclidean inner product, of course. Okay, so far so tricky. And then the final calculation is that on the imaginary Lorentzian contour here, that's to say with the time-like vector field being an imaginary vector field and the others being real, then you can calculate, and it's not entirely trivial, but there's some work to do, that the D, so that's the Lorentzian Dirac operator, but on this imaginary contour, is just I times the Euclidean Dirac operator. So that's a good calculation. And then finally, there's this calculation of the action. You take the Lorentzian action here on this imaginary contour, in other words, using the imaginary Dirac operator, and you write a formula for it here. And I've done that using Lorentzian fields and Lorentzian everything. So normally you'd write psi, the inner product of psi d psi. But I want to emphasize that because this formula here is sesquilinear, it's antilinear in this slot. So I'm going to write it as J, the charge conjugate of psi bar, and psi bar is just the charge conjugate field of psi. So you can always think of a complex field as you can double it up as twice as many real fields. So I can think of psi and psi bar as independent real fields. So from the point of view of quantum field theory, this is a better formula for this. And as we know that when you calculate this, you get a determinant in quantum field theory. And now I want to see what happens when I go to my imaginary contour and Euclideanize it. So here we go. I want to switch this Lorentzian product for a Euclidean product, and I get to put a gamma naught in the formula there. My Dirac operator becomes I times the Euclidean Dirac operator. My volume form becomes minus I times the Euclidean volume form. So the factors of I cancel. The gamma J becomes the Euclidean charge conjugation operator, JE. And again, there's a page of calculations to check that it's got all the right properties, and it does, they work out. Then you get this formula here for this. There's a sub E missing here. This is the Euclidean inner product here. And then this is precisely Con's formula, which I had right back at the beginning here. Wherever it was, yep, here. So this is Con's formula here, where you take the Euclidean fermion action with a J in it. And the reason there's a J in it is in Euclidean signature, if you take a left-handed field and you Dirac it, you get a right-handed field. But this pairs in the Euclidean inner product with another right-handed field. But unfortunately, psi here is left-handed if you have a chiral theory. But J psi is right-handed, so that is non-zero when you put the J in the formula there. So this was Alan Con's formula for the fermionic action. And here you see it coming out here naturally when I do this analytic continuation here. Although what you have to recognize is that in Con's formula, what you've done is you've doubled the Hilbert space size by omitting the fields and their conjugates as independent real variables, and that's why there's a psi bar in this formula here. It's a bit tricky. It's the doubled field in that double. So right. So what Con says is that you should calculate a Pfaffian of this thing here, which is a matrix of twice the size, an antisymmetric matrix of twice the size as the previous matrix. And then we know the Pfaffian of a matrix antisymmetric matrix of twice the size is the determinant of the block in one of the corners of the matrix. So it all turns out to be the same thing, and there we are. That's my explanation of Euclideanization. So to summarize, I've worked out a framework for proving this formula here. I think the functional integral aspects are somewhat heuristic and require reformulation to some theory in which you respect the Planck scale before it would make any sense. But the bits that do look like the action of gravity, scalars, even fermions, do in fact correspond very closely to the Lorentzian physics on the one hand, and a sensible geometric notion of what we think of as Euclidean physics on the other side of the formula. And indeed, one recovers something that looks like Alan Kahn's version of the spectral action formula for the fermion field, and at least, and possibly for the rest of it, although I have to say it's not entirely clear what exactly how you do quantum gravity with this bosonic part of the formula there. So I think that needs more work. But this part of the formula seems to be quite secure. Okay, so I've come to the end of my exploration of Euclidean quantum gravity. And so that's it.
Okay, thank you very much, John. So thanks for the talk, which despite, the problems in the very beginning and the problems of joining it, so I apologize once again. We enjoyed very much, and now it's time for questions and discussion. Please, just raise your hands so I can see it, or just ask the questions straight ahead. Fedele, please.
Yes, you see me. Hello, John. It is just a comment. I find your talk very inspiring, and I never liked weak rotations. You say that I did. In fact, you quoted me for the paper in weak rotation, but I always thought that the interplay between Euclidean and Lorentzian is more profound. However, the comment I would like to add is that there may be, for Kahn's spectral action, another element, and this may be the twist. Because when what you call the J there, is after all a twist by gamma zero, which in the Euclidean can be any of the gammas, and then you can write it in whichever way. So I'm always sorry that not so many people are working on Kahn's spectral action. In fact, we are quite few. But there are lots of little elements. There is the model of Andrei, another of the few that well, we are not really 3 or 4, but there more manpower could be useful on the of these models without fermion doublings, and even there are echoes there. I feel that there are all these sparse things, and probably more understanding will put things more and more together, because I can see throughout the years how things are somehow getting together. When we did the fermion doubling in 90 something, and then you came and you related it with the Lorentzian and Euclidean, and so the comment is that I think that we should probably study more in general, because there are loose ends, and every time you take 2 randomly chosen and you put them together and you find some connections. So now I find your talk very inspiring, of your treating the Euclidean not in a standard way. After somebody was commenting it, I was taught this is the weak rotation. Yes, in the end, it's always you have a Lorentzian and a Euclidean, and you somehow have to change one direction. But your point of view, which is actually I was surprised to see is the original one. Again, another lesson to learn. Probably going back to the original ideas is a good thing. Anyway, this was just a comment, and I talked already too much. Thank you.
Thank you.
John, anything to add?
No, nice to hear from Fedele.
Okay, so then we go to the next question. I'm sorry with the pronunciation, Muxin Han.
I just want to ask, how about the contour, the part of contour at infinity in the integration? You weak rotate, and there should be a part of contour like your diagram. There should be a part of contour which is part of the circle at infinity.
Yeah, that's right. So there's probably two things. One is what happens when the geometries are very small, so at the Planck scale, and the other thing is what happens when the geometries are very large. And so, for example, if the frame field degenerates, and they're both sort of extreme ends of this integration contour, and certainly I can't really answer the question about what happens at the Planck scale, because I think, well, you can look at the Einstein-Hilbert action, but I don't think that really gives a sensible answer, because that surely isn't fundamental at the Planck scale. So I'm not really sure that it's useful trying to stare at the Einstein-Hilbert action and ask how it behaves at high energy near the Planck scale. The other end, when you're looking at very small frame fields, which correspond to points that where some directions that are very large, then that's a bit more realistic, and one should study that. But it looks quite complicated, and it's bound up with the question of what happens with the cutoff in your theory when the frame fields become degenerate. And what happens, you see, is the normal formulas don't work for a degenerate metric or frame field. So it's not entirely clear, in which direction you're taking these limits and so on. So I have thought about this for a while, but I've sort of parked the question of it's really a question we need to come back to when we have a better way of formulating the quantum gravity functional integral, which I think happens in non-commutative geometry. We've got some very good ways of doing that, where we can make exact mathematical sense, and then we can go back and re-ask that question there. And I think that's what I want to do. Okay,
so maybe so you mean so far the behavior at infinity of the integration domain is not clear. So at the moment you are not sure whether that part of contour giving the contribution from that part of contour is negligible or not. That's something you are not sure at this moment.
Yeah.
Okay.
Well, for me, you see, large frame fields means the metric is very small, because remember, my frame fields turn into the inverse metric. So large frame fields are very small space-time. So that's the Planck scale. So what you're literally asking me is what happens to the Einstein-Hilbert action as space-time approaches the Planck scale. Well, if you have, if you look at the cosmological term, it becomes very small because the volume is small at the Planck scale. If you just think of a small Euclidean universe, well, it's a sphere or something, and it gets smaller and smaller, so the volume goes to zero. The Einstein-Hilbert also goes to zero. It does depend a bit on which directions become small and so on. But higher curvature terms definitely become very large. So if there are any higher curvature terms, then that phase factor will oscillate more and more as you get off to large frame fields, which is what you want, because that's what you want for the integral to converge. Remember my 1/w prime factor, that will become large.
Okay, I see. All right, thank you.
Thank you very much. Any more questions? Let me ask one question, John. I mean, this is, the spectral action, I mean, is computable in the Euclidean version.
Yeah.
But there's been some progress in the computation of the spectral action, only for gravity, so not the full model or not the including connections, and for the scalar operators like for the Laplace operator. But in the Lorentzian setup, using the quantum field theory techniques. So do you expect, I mean, the sort of the procedure of passing from the Lorentzian to Euclidean should be something that you compute this action Euclidean, you compute the action Lorentzian, and the passage should pass from one to the other?
Yeah, that's the hope.
That's the hope. Okay.
I mean, so we have, I mean, we know established physics, and so we can take that heuristically and then do the contour rotation to Euclidean physics and get heuristically what the Euclidean physics should be.
Should be.
But we can also then start at the Euclidean end and define perhaps precisely some sort of functional integral over Euclidean non-commutative geometries, for example. And then we can hope to go backwards and see what it buys us in the Lorentzian framework. So what I want to do is then run this process backwards and say, well, okay, if I do this thing in the Euclidean thing and I get a convergent integral, what oscillatory integral does it buy me in the Lorentzian framework? And it's, you know, hit or miss. It may hit established physics or it may be wrong, you know, but it'll be an experimental process to see what we can get.
Exactly. Okay, thank you. Any more questions? And I don't see anybody raising hand or speaking up. You know, this is always sometimes, you know, somebody might be speaking up, but could be muted, but let's hope not. So in that case, we thank very much John by applauding, you know, virtually or just, you know, turning our, unmuting ourselves. So thank you very much, John. This talk was recorded, so it will be available on YouTube for anybody, for people who might have missed one part. So thank you very much. I stop the recording now.